So hello everyone, welcome to this new video. So as you guys have shown us a huge support for the video related to electromagnetic theory passing package. Okay, so here I'm going to provide you all now the important stuffs and some of the important, very important concepts related to the tomorrow's exam for ECE stream for fourth sem, that is Principles of Communication System, in short PCS. Okay, so we are going to provide module by module all the important stuff from all the modules. Okay. So please do watch this video till the end. And the PDF for this is no, we are not providing any kind of PDF, guys. Okay. So please don't comment about any PDF things. Okay. It's a loss for us because if we provide PDF, our viewership would be becoming less. So that's why PDF is not provided. So please do watch the video. Okay, it is beautifully presented. Okay, handwriting is also neat. You can pause the video and note it down, and if you note it down, it's beneficial for you only. Okay, if you practice it, so that's why you can make your own hand notes. Yeah, so now let's start module by module, all the concepts. So one important question from module 1 is definitely the first question, that is define probability and illustrate the relationship between sample space, events and probability. So this is a sure question. Okay, so this question you need to be knowing here. So here is the notes for that probability. So it is beautifully mentioned. This is the definition here of 6 lines. Then the relationship between sample space, event and probability, and the formula for probability is given as number of outcomes in E divided by total number of outcomes in S, that is sample space. And here is the beautiful pictorial representation of how the relationship between sample space, event and probability here. So here this outer layer is completely a sample space. Okay, and here it is the E that occurs inside the sample space, and probability is the relationship between this event and sample space. Okay, yeah. So this one question is one must read question, that is define probability, illustrate the relationship between sample space, events and probability. Along with that, they might be asking what is conditional probability and prove that P of B on A is equal to P of A on B into P of B by B of A. Okay, its definition is provided here, and the derivation part here it's not there, but you can refer our model paper solution video where we have provided this derivation. Okay, it is available in our channel. This question is also very important. Okay, one is define probability, illustrate the relationship between sample space, events and probability, and second one is what is conditional probability and we need to prove this. Okay, so one more important question is related to define autocorrelation and cross correlation functions and infer the properties of autocorrelation. That is, we need to be defining what is autocorrelation and cross correlation. Here beautifully it is defined. Okay, and this is the relationship for autocorrelation mentioned here. You can note it down. Okay, and here the cross correlation it's defined here, defined here. Okay, then definition along with the two discrete signals, that is continuous as well as discrete signals, and these are the set of equations for both continuous as well as discrete signals. You can note it down, and here are some of the properties of autocorrelation functions. One is symmetry, maximum to zero lag, non-negativity, even function, periodicity, real values for real signals, and position semi-definite. Okay, so all of these points, mention it and write a few lines related to that, few lines. Okay, and one more important question from this module is, it is a fixed question. It might be asking because these questions are there in model paper as well. Also these questions are multiple times repeated, so you need to be learning this. Okay, that is define correlation, covariance and correlation coefficient. Its definitions and all are mentioned here. Okay, you can see it. One is for correlation, covariance and correlation coefficient. Okay, and here is the relationship between all of these standard deviations and all of these all of these are interrelated to each other by this formula. And here are the standard deviations mentioned, that is sigma x and sigma y. Okay, it gives dependency between the random variables x and y, and here are the relationship with sigma relationship between standard deviation x and y is equal to 0, equal to 1, and it is between 0 to 1. What and all are the occurrences that are going to happen. Okay, it's mentioned beautifully. You can pause the video and you can refer it. Okay, yeah. So these were the four important questions from module 1. So now let's discuss some important questions from module 2. Yeah, so the name of the module 2 here is amplitude modulation, as you might be knowing. Okay, and some of the important questions from amplitude modulation is, they might be asking to define amplitude modulation along with the waveforms, that is message signal, carrier signal, and AM modulated signal. Okay, this question I guess they won't be asking, that is what is modulation in communication system. So directly define amplitude modulation. Here it is defined. It is a type of modulation where amplitude of the carrier signal is varied with respect to the amplitude of the message signal, keeping the frequency and phase constant. Okay, and this is the relationship for AM wave. This is a simple formula. Okay, so this question is very important related to amplitude modulation, so please note it down. Okay, so one more important question here is, it's related to types of modulation. Okay, yeah, so these are the few types of modulation here: amplitude modulation, frequency modulation, phase modulation. Okay, and pulse width modulation, if you want you can write. Okay, yeah, this quadrature amplitude modulation is not required. The four important kinds of modulation, it because it's repeated multiple times repeated. Explain the types of modulation. One is amplitude modulation, its definition along with the few properties and application. Frequency modulation, one definition, one property, and one application about where it is used. Phase modulation, definition, property, and one of the applications. Okay, about where it is used. And pulse width modulation also same thing. So this is one more important question related to types of modulation. So you can note it down. So one more question is, yeah, this question is again multiple times repeated. That is, explain the principles of amplitude modulation along with equations, waveforms, and frequency spectrum. Okay, yeah, this is very important. That is basic principles of amplitude modulation. One is modulating signal, one is carrier signal and resulting waveform, that is called as the AM modulated signal. Okay, modulating signal means we start modulating signal denoted as, it is denoted as M of T, which represents the baseband message signal or audio signal. It does not has a constant time duration. It varies over time. Okay. Second is carrier signal. It is denoted as C of T. It is a high frequency sinusoidal wave, and it has a fixed frequency along with the fixed amplitude. Resulting waveform is a mixture of these two signals, that is a multiplication of these two modulating signal as well as carrier signal, that is called as AM modulated signal. Okay, yeah, it is represented as S of T, and these are the three signals, that is message signal, carrier signal, and amplitude modulation signal. You can note it down along with the mathematical expressions for FM, FC, and AM. Okay, then AM after splitting the values of FM, FC. Okay, and this VC sine omega CT is for carrier signal, and this is for lower sideband, and here this term is for upper sideband. Okay, you can note it down along with the frequency spectrum. Okay, this is the frequency spectrum or frequency domain, where we have given the frequency domain of bandwidth, that is one region is FC minus FM, FC plus FM, and total region of this bandwidth is called as 2 FM. Okay, that is twice the frequency of message signal. So this is one important question. One more important question is, explain modulation index and percentage of modulation. So this is again very important, multiple times repeated. Related to these problems would be asking, they would be asking the problems to find the modulation as well as percentage modulation. We should know that the definition, and this is the fixed formula for modulation, that is Vm by Vc. Percentage of modulation is Vm by Vc into 100. Okay, modulation index, along with that the percentage of modulation. For before that, modulation index in a particular time domain, you need to be finding its value. Okay, it has a fixed value, where this is the V max, that is from constant origin to the highest amplitude, it is mentioned as V max. Okay, and from where the waveform starts, it is called as Vc, and where the waveform would be reaching its peak and coming down, that region is called as Vm. Okay, and where the Vm minus Vc is mentioned as Vmin. Okay, so these are the set of equations here. I've derived it beautifully. You can note it down. Okay, yeah, and one more, this derivation is not important, but some of the formulas I'm going to tell you all in order to solve problems which you need to be knowing. One formula is for PC, that is carrier power. Okay, it is represented as Vc square by 2R. Okay, this is the formula for carrier power here. Okay, and here this is the formula for total sideband power, that is PSB, is given as PC into M square by 4, where M stands for modulation index, and you know that modulation index is Vm by Vc. Okay, and here this is the formula for total power, that is P total is given as PC into 1 plus M square by 2. This power is, this AM power is also very important. So these three formulas, PC, PSB, and P total, please remember it, because uh, of this formulas the problems would be asking. Okay, yeah. So here one more important question is related to the draw the amplitude modulated waves for the different values of modulation index. That is, whenever the modulation index has a fixed value, what would be the resulted waveform? Okay, that these kind of questions they would be asking. That is case one. We should write when m is equal to 0. What is the expected waveform we get for s of t? Okay, the amplitude of the message signal is 0, so Vm is equal to 0. The unmodulated carrier is present, see we won't get any waveform, that is a constant straight line. For case 2, just consider the value of modulation index as 50%. This is the resultant waveform. Okay. For 100% modulation, the amplitude is approximately 0. Here it reaches, and here it approximately it would be touching the axis here. So that's why it is approximately 0. Okay. And here, in case of when amplitude is more than 1, that is more than 100%, over modulation occurs and overlapping would be taking place between the signals. Okay. Yeah. So these are the 4 cases, and this is one more very important question. Pause the video and refer it. Okay. And here are some of the example problems here. Question number 1, where a direct formula for problems related to formulas which I have discussed. Okay. You can pause the video and refer it. These are beautifully. I've solved it here. I'm just going to scroll down slowly, and you can copy down the question and pause the video and refer all the problems very clearly. Okay. So these are the sub questions here. 3, 4. All the solutions are provided. Okay. 5 and 6. Okay. So these are the very important. And one more question is related to explain the following signals with waveform, that is double sideband signal, single sideband signal, and double sideband suppressed carrier. All of them we need to be explaining with waveforms. Double sideband signals, it takes in both the half cycles, that is positive half cycle and negative half cycle. Okay. Yeah. And this is the waveform or the single sideband signal, where the uh, variation takes place only in the positive half cycle and the amplitude of the negative half cycle remains constant. Okay. Yeah, so please do note down these two things, and along with that, we have given also the advantages as well as disadvantages. Sorry, only the disadvantages of the double sideband and single sideband. You can note it down. Okay, and some more important questions are very important. Okay, that is related to one is square law modulator. Okay, its circuit, its equations, along with that few of the explanation, along with that the waveform, that is how it is going to work. Square law modulator. Second one is diode modulator, its circuit, some of the explanation part, and all the waveforms, that is message signal, carrier signal, first amplitude change signal, second amplitude change signal, what and all are the changes which we see in case of amplitude. So this is for a single sideband signal, okay? And this is the final waveform which we get. And the third one is transistor modulator, its circuit, waveforms, and some of the explanation. Okay. And other two are high level collector modulator and series amplitude modulation. Okay, these two are the circuits and some of the explanations we have provided. So pause the video and refer it. Okay. So one more important question is related to lattice modulator. Okay, this is again a very important question. Okay, the simple circuit. Okay, and along with that, we need to be writing the circuit for positive half cycle and negative half cycle. That is, what is the condition for diode? Okay, those things you need to be mentioning along with the working of during positive and negative half cycle with some sub circuits. It is a must. Then message signal, carrier signal, and this is the modulated output in case of lattice modulator. You should note it down. So these are the concepts of module 2. Now let's discuss about module 3. So from module 3, one question is fixed, that is it should be coming from phase lock loop PLL, that is define PLL and explain the basic block diagram of PLL along with capture range and lock range. Okay, capture range and lock range. So this is the definition here they are provided for phase lock loop. Block diagram, what and all are the components present in block diagram, that is phase detector, low pass filter, voltage controlled oscillator, and feedback path. Okay, feedback path is not necessary. All these three components, that is phase detector, low pass filter, and voltage control oscillator, try to draw this in series and name this and in each block we need to be mentioning the names of phase detector, low pass filter, and voltage control oscillator, and the path which is connected, that path is called as feedback path. Okay. So all the definitions of phase detector, low pass filter, voltage control oscillator, it's mentioned here. You can note it down. Okay, along with the capture and lock ranges, capture range and lock range. Okay, that is the range of frequencies over which the phase lock loop acquire lock with the input signal. With the help of input signal, the phase lock loop would be acquiring the lock range. Same goes with lock range, that is range of frequency over which PLL can maintain the lock range. Okay, maintain the lock once it has been acquired. Okay, once it has been acquired from the capture range, in order to maintain it, in order to maintain the signal of the phase lock loop, okay, we use this lock range here. Okay, so this was all about the capture range and lock range. One more important question is definition of signal to noise ratio. Okay, this explain different types of external and internal noise. Don't read this definition part of signal to noise ratio. You need to be knowing definition along with the relationship of SNR, how it is given, because SNR is equal to P signal divided by P noise, and it is expressed in decibels. This is the formulas for that if we convert it into decibels. So please note it down. You related to these problems would be asked. Okay. So one more important question is, this is a very fixed question and multiple times repeated question. You need to be learning this question, that is develop a code to generate the NRZ and RZ pulse. Okay. So this is the code for that NRZ and RZ pulse, that is one data they would be giving binary number. Okay. How this would data would be drawing that waveform here, that is 10110010. For that, we need to be taking some samples per bit in a particular heat, then mention all the quantities and write the simple MATLAB code. Okay, so this is that code, you can note it down. Okay, and one more important question is identify the noise suppression effects of the frequency modulation. Okay, this is again very important. The some of the noise suppression effects are capture effect, noise immunity, de-emphasis, free emphasis, wideband characteristics, and frequency discrimination. All of its some of the points related to all of these, you need to be writing it. Okay, yeah, and some of the problems and also this question is important, that is develop a code to generate the and plot the eye diagram. Okay, this code is very important, you can note it down, this code. Okay, and these are few of the problems here mentioned in this PDF. So I'm just going to scroll it down, just note it down. Okay, yeah, so these are the few problems related to frequency deviation and improved output range of signal to noise ratio. What and all are the formulas, and this beta range is also called as signal to noise ratio constant. So yeah, please note it down. So let's discuss the further modules, that is module 4 and module 5. So yeah, one more question that is very important, with the neat diagram explain the operation of super heterodyne receiver. Okay, so this question is also multiple times repeated question. Okay, so yeah, please note this block here. What and all of the components use RF amplifier, mixer, IF amplifier, limiter, discriminator, AGC, that is automatic gain control, and AFC, that is automatic frequency control, de-emphasis circuit, audio amplifier, and the speaker that is generating the output. Okay, beautiful, it is explained here. Some of the points you can note it down in short. Then yeah, these and all. Then this question is again important, that is what are the advantages of digital signal over analog signal. Some of the advantages you need to be writing: a resistance to noise interference, accuracy and clarity, efficient transmission storage, long distance transmission, security, versatility, signal processing, cost effectiveness. Okay, so these are the few advantages over analog signal. Some note it down. Okay, and these are the few of the signals. Like this, they would be asking to write the following signals as some sub questions. That is here in this case they are mentioned to write the one simple message signal, simple carrier signal. So this is one simple frequency modulated signal. This is the pulse width modulated signal where the amplitude would be remaining constant, and width of the message signal is changing. Okay, with respect to carrier signal, width of the message signal is changing. Okay, then this is the simple diagram of natural sampling. Okay, flat top sampling means this top would be remaining flat, that is a straight line, it won't be changing. Okay, yeah, so that was all about flat top sampling, and this is the final waveform is about pulse position modulation. Okay, so this question is very important. Like this sub question they would be asking. Okay, so one more question is related to FDM receiver or FDM transmitter. Okay, this code is also very important. This question is very important. You can note it down. And one question is related to this type of question. That is, they would be giving one simple bit sequence. Okay, that is one bit sequence they would be giving, and we need to draw the resulting waveforms for unipolar NRZ, polar NRZ, bipolar NRZ, unipolar RZ, polar RZ, bipolar polar RZ, along with the Manchester code also. Okay, yeah. So these are the simple waveforms for unipolar, polar, bipolar, unipolar RZ, bipolar RZ. You can note it down. For in case of NRZ, the full amplitude, the full frequency would be taking part place from one position to other position. Okay, full cycle. Okay, in unipolar from 1 to 0, the value of A, when it becomes 0, it is -1. In place of, in case of polar, when it is 0, the value of A would be 0. In case of bipolar, it is once it is 1, then it is 0, and one more times when it comes to 1, it goes to the negative half cycles 1, then again 1. So upside, then constant 0, then 1 downside. Once it is up down, in this sequence it would be going. Okay, so unipolar RZ is the same thing but only for half cycle. Okay, yeah, so you can note it down, these waveforms. So one more thing is the derivation of this SNR, signal to noise ratio, in case of a uniform quantizer. Okay, this question is also multiple times repeated question. What is quantization noise, and derive the expression for a SNR of a uniform quantizer. So write the definition of quantization noise and the relationship of signal to noise ratio with respect to quantizer, that is sigma x square divided by sigma a square. And these are the full derivation here. It is derived beautifully. The each step you would understand it by seeing the derivation only. And final expression for uniform quantizer for signal to noise ratio is 6v by w minus 7.2. Okay. Yeah. So again, with the neat block diagram, explain the generation of pulse position modulation. Okay. Yeah, explain the pulse position modulation with the neat diagram here. We are using here one comparator, along with that one monostable multivibrated is directly given to the PWM output. Whatever is generated from the comparator is given to a monostable multivibrator, and the resulting output is we get is the pulse position modulated signal. Okay. So here for monostable multivibrated, we use the IC 555. You can mention that. Okay, IC 555 is used in case of a monostable multivibrator, and this is the output generated for PWM and PPM. So one more important question from this module is explain sampling theorem. So this question you have to be learning. Okay, this would be coming for around in around 10 marks. That is, explain sampling theorem in brief, its statement, its relationship, and its proof with the different kinds of waveforms. And you can explain in your own words about all the samplings, that is natural sampling, flat top sampling, all of them you can express it. So this is one statement related to a sampling theorem, and this is the relation here: Fs is greater than or equal to 2 times Fm. Proof: some of the signals, okay, in individual pulses in positive and negative half cycle using the multiplier. And this is the derivation of a sampled signal using the trigonometric Fourier series representation. We need to be deriving it, so it is beautifully derived. You can pause the video and refer it. And these are the three different kinds of signals, that is oversampling when Fs is greater than 2 times Fm. So this oversampling takes place here. So when Fs is equal to 2 Fm, perfect sampling takes place without any gap here. And when Fs is less than 2 times Fm, the undersampling takes place, where one sampling is getting overlapped with other sampling. Okay, so these are the three diagrams you need to be mentioning. Yeah, so that's all. So these were some of the very important concepts that I've just brushed up. Okay, so yeah, please do like, share, subscribe, and also comment down your opinions about how this video was useful. Okay, so please take this video as a reference, and whatever questions I've displayed it, pause the video and take it down. Okay, the PDF is not available, so sorry for that, but you can take these notes. Yeah, so that's all the best for the exam, guys. Thank you.